And first I start with Node-RED. Node-RED is a visual editor that you can open in the browser. Here you can see it. And you can access it in the local network of this APS over the follow IP address. And it's based on Node.js. And Node.js is a JavaScript runtime environment, which is lightweight and event-driven, and it's used for servers and IoT applications. And Node-RED is a toolbox for IoT projects that's based on Node.js. And you have nodes, for example, here a WebSocket node, and you can drag and drop it here in the field, and then you can connect it with other nodes. And so you have your own logic for your project. And it has a wide range of nodes, for example, MQTT, OPC UA, or HTTP. Node-RED is used by fischertechnik as an interface between MQTT and the PLCs. For example, the HBW only has a PLC and doesn't get the messages from the MQTT broker. So in Node-RED, they have created a flow where both signals are passed and then react on them each other. And we built an own flow where we take the data from MQTT and the PLCs and then send it over the WebSocket server and the real server to the WebGL, to the client. And here you can see the flow. And it has three main parts. The first one is for the PLC, and there you have listener nodes. I don't know, can you read it, or is it too small? It's the second blue node, and we need it for every PLC. And in this listener node, we monitor variables, but send them if they are changing, also a Boolean from true to false or from false to true. Then we have inject nodes. Those are the first blue nodes. And here you can define which variables you want to monitor. And then you have this table. There you can give a name for the variable. And then you have to give the identifier. And the identifier you can get from the OPC UA server or the UA expert. It's a software that you can use for that. And then you have to give this identifier in the table. After that, we have two function blocks or function nodes. And there we create a JSON. And the JSON is sent over the WebSocket server to the WebGL. And this JSON contains of two variables. The first name is variable name. It contains the name of the variable. And then the value, this could be a string, an integer, a float, or a Boolean. But in the WebGL itself, it's handled as a string. Then for the MQTT, we have an MQTT node. It's the purple one. And that we can get data, we need to subscribe to topics. So every sensor has their own topic and every station. And we have three topic groups. The first one is for the FTS or HGV, those vehicles. And we have two. So we have for everyone an order topic and the action topic. And in these topics, the drive information, the route is inside the JSON. Then we have the stock. The stock shows the stock of the HBW. And then we have the last one, it's for the DPS. And there we extract the position data. After the MQTT block, we have a switch to separate those data to handle it on their own. And here you can see the data handling. We have function blocks, and they transform the received JSON from MQTT in an output JSON. It's the same output JSON as for the PLCs with variable name and the variable data. Why are we doing this? First one, we want to reduce the data traffic. We only send the necessary variables. And for the HGV, it's easier for us to transform it so it can handle its the programming in the WebGL in Unity is easier for us. So we have the perfect data structure to implement this. Then by the DPS, we take the robot positions and the workpiece color. And there we have also a switch to separate them again. But there's one problem for the position data. If this message is coming, it doesn't correspond with the real position of the robot because there's a delay. And so we have a lot of delay blocks to capture those delays. But the delays internal are not constant, so it's not often a synchronous movement. So we are behind or we're in front of the real robot. And that's something that you can improve by programming the TXT controller for the robot to send the real position data. Then the next is the WebSocket server, which is also shown here. There we have an in and out node, so we have a bidirectional communication. We send data from Node-RED to the WebGL. It's the sensor data, but also can receive data. It's important for you if you want to control the real system from the WebGL. And we also implemented a ping-pong signal because we have a WebSocket connection, and the browser doesn't like it when the connection is too long open and no data is sent, or if only data from the server to the client is sent. And so we have a ping-pong signal. The WebGL sends ping, and we send pong back, and then the connection is kept alive. Then the server, it's behind this wall. We have a simple Nginx server with a reverse proxy for the WebSocket connection. Also from here over this router to the router where the server is, and then to the server, and from there to the WebGL. Then we host the two WebGLs, the WebGL for the real system and the simulation. And to do this, we have a port forwarding from this router to this router and to the Raspberry Pi. This Nginx server is a local server, and we expose this to the internet over a Cloudflare tunnel. It's really safe. We don't have to open a port or make port forwarding, and it's also handled the encryption over SSL. So it's the easiest and cheapest way to explore the server, expose the server. And all this software is deployed in Docker containers. It's the best way to do it. It's platform independent, so you can use it on your Mac or on your Windows PC if this server is down or broken. And yeah, it's the perfect fit for that project. And then we have the next